So back to this idea of the statement of inquiry, remember that scientific models are representation. So again, we need to think about the scientific model of the enzyme, and that allows us to understand better the structure and then the function of the enzymes. And enzymes obviously are vitally important to make sure that the chemical reactions of life can take place. So these are our driving questions, and I asked you to think about these at the end of last lesson. So a factual question, which is obviously much easier to answer. How do enzymes work? So we know that enzymes have got a very specific shape, a specific active site, and it's this idea that the shape of the active site which fits with that of the substrate molecule, which allows the enzyme to do its job. And when that fitting together takes place between the substrate and the enzyme, we can lower the reaction, the activation energy required for the reaction, and the reaction can proceed. So enzymes work, and we can model this in terms of one theory called the lock and key hypothesis, or the lock and key model, which we talked about in previous lessons. Now that brings us nicely onto this next question, because this is a conceptual question, and it says here, what is a paradigm shift? And I talked to a few of you at the very end of the lesson last week. And a paradigm shift is a shift in the way in which we think things are. So it's a shift in our belief system. And in terms of science, it's a shift in what we think is true in terms of a scientific model, for example. So the lock and key model of enzyme activity is actually being replaced by a more sophisticated model called the induced fit model. And the induced fit model talks more and emphasizes more that when you have the interaction between the substrate and the active site of the enzyme, that's a chemical phenomenon, not just like a key and a lock. So it's not just shape, it's chemistry as well. So a good example of a paradigm shift in the context of this unit is looking at the shift from the lock and key model of enzyme activity to the induced fit model of enzyme activity. And this is actually a little bit beyond what you're required to know for IGCSE, but it's interesting. Now, the debatable question is much more philosophical and much more challenging in terms of answering. But the things that we might consider here, to what extent can we observe chemical processes in a cell accurately? Now, obviously, the molecules which are reacting within our cells, they're far too small to be seen. We also need to appreciate that chemical reactions occur when chemical bonds are broken and then reform between these molecules. And again, we can't see this by the general observation of using our eyes, but we can make observations which are different. So in chemistry, sometimes you're asked to look for the appearance of bubbles. You're asked to look at a chemical change, which is the same in biology. So what we need to do in order to track whether or not a chemical reaction is taking place is that we need to make sort of indirect observations. So there's a lot of creativity that is very important in terms of scientific design, which allows us to measure chemical processes. Now, how accurate that is depends on how good your scientific methodology has been designed. And we're going to look at that in some later in this section. Also, I want us to think about that in science, innovation is really super important, because innovation, for example, in terms of technology, we are constantly thinking of ways in which we can measure the rate of a reaction by using technological solutions. So we can make machines which allow reactions to be seen that are too small for us to view by eye. But again, that's a very philosophical question. Do make sure that you've got something noted down in your booklet about these questions, though. And let's move on to unpacking this syllabus statement in a lot more detail. And what we have to understand here is the function of enzyme in terms of its temperature. So we already know from previous theoretical lessons that if you increase the temperature, what happens is that the kinetic energy of both the substrate and the molecule increase. So the more kinetic energy there is, the more chance that the enzyme will collide with the active site of the enzyme, and the faster the rate of reaction will take place. However, we also know that if the temperature is too high, the actual jiggling about, the kinetic energy of the enzyme itself gets so great that the enzyme starts to change shape. That's called denaturation. And if we denature our enzyme, that means it's kaput. It can't be used at all. So if we want to understand what might the optimum temperature be? How could we do this in practice? And the example that we're going to look at here is this one here. So we're going to start off with the substrate, which is starch, and we're interested in the enzyme, which is a carbohydrate specifically called amylase, and amylase is very specific to starch, and it will break that down into maltose. And remember that maltose is it's modeled here like this because it's a disaccharide. It's got 2 sugar units. We can also have maltase, the enzyme, breaking this down even further into glucose. Now, amylase is found in your saliva. That's called salivary amylase. It's also found in your pancreas, pancreatic amylase. But amylase is the enzyme which is very specific to the molecule starch. And when we break down starch, it's going to form maltose, this sugar here. If we're interested in looking at the temperature and we want to look at this as what we call our independent variable, we can change the temperature in a laboratory by either using this piece of kit here. This is called a water bath. Or we can do it in a kind of old-fashioned way. We can take a beaker of water and we can heat that up with a Bunsen burner, and we can take the temperature of the water and then allow our reaction to take place within this kind of setup, our water bath. This is a much more crude experiment. Now, this is looking at not starch, it's looking at a slightly different experiment, but the visual is what I'm interested in you thinking about here. So we can deliberately manipulate the temperature of our reaction by using a water bath. So we could place the starch and the amylase inside this water bath, which is preset to a particular temperature, or we can heat up water and then have our reaction taking place in a test tube like so. So the syllabus statement is understanding how the function of an enzyme can be affected by changes in the temperature, including changes due to a change in the active site. So we've got theory and we've got some practical analysis here. Now, I am assuming that you know all about scientific variables, and if you don't, and if you can't remember stuff, I would pause the video here, go into the Google Classroom and play the video which reminds you about scientific variables. But the first scientific variable that I want us to think about in our experiment is the independent variable's temperature. So what we're doing in our experiment is that we are deliberately changing the temperature, and at that temperature, we're trying to establish how quickly the rate of amylase breaking down starch can take place. So the independent variable is the variable that we deliberately change because we're interested in finding out more about temperature. The dependent variable is going to be the rate of reaction, and the control variables of all the other things that we need to keep the same, okay, other than changing the temperature. And the independent variable in this case is temperature, and we're going to use water baths, or in this case an ice bath, which is preset at these temperatures. And if you look in your booklet, it outlines the practical procedure that we're going to use here. So its first syllabus statement, what we're interested in is this experiment, and we're interested in looking at the independent variable temperature and tracking the rate of reaction if we change this independent variable of temperature. How do we measure the rate of reaction? So going back to this idea that we can't see it proceeding because starch is a solution. The amylase is a solution, maltose is a solution. They're all colorless, so we can't see what's going on. So how can we know? Well, we are going to be innovative in terms of the design of our experiments, and this is really what we're going to look at. So the dependent variable is the rate of reaction, and the rate of reaction is going to be about how quickly the reaction takes place. And we measure this, in fact, as using this particular equation here. It's 1 divided by the time taken to digest starch. Rate is always a measurement per unit time, which is why we divide by time. So if we've got a set amount of starch that we need to break down, right, what we're trying to do here is, well, how long does it take for that set amount of starch to get broken down? And then we can calculate the rate of the reaction. But how do we actually do that? Well, we do it using the iodine test. And you're familiar with iodine from previously in this unit. And iodine is the chemical which allows us to detect the presence or absence of starch. So remember that if iodine is mixed with starch, it will be black. So the iodine changes its color to black if it's in the presence of starch. If there is no starch present, then the iodine will be brown. So we can make use of iodine to track the rate of our experiment. So what we've got here is the water bath, and the water bath has got here the amylase solution and the starch solution. So the first thing I'd want to do is make sure that I've I've measured these two things out and I've put them in the water bath, and I leave them in the water bath until they're at the temperature that I want. And once they've been at that temperature for a little bit of time and the temperature has had the impact on the enzyme, what I can then do is mix these two things together, which is what we see here. So I'm going to mix them together, and then what I'm going to do, keeping it at the same temperature, then what I'm going to do is I'm going to sample out of this mixture a little bit, ideally measuring a set volume of this mixture, and I'm going to place it into onto a spotting tile which has got iodine solution already measured out. So when I mix them together and I take my initial sample, at time 0, I'm going to expect this well here with the iodine to be black, because obviously I've just mixed them together. So at time 0, it should have starch present and it should be black. And then what I can do is I can sample it 30 seconds later. And if it's black still, I can say, well, okay, there's still starch present. The digestion process is still taking place. And I carry on with that every 30 seconds, every 30 seconds. And at some point, what we're going to find is that when we take a sample from here and we add it to the iodine solution will be brown. Now, if the iodine solution is brown, that means there's no starch. And if there's no starch, then we can conclude that all of the starch has been digested. So we finish the reaction, and then we can count up how many wells were black and how many were brown in order to calculate the rate of reaction. So in this particular experiment, I'm deliberately changing the temperature. So I'd set this up at, let's say, 20 degrees. Then I'd set it up at 40 degrees, 60 degrees, etc., etc. And at each temperature, I'd want to do repeated tests. And the repeats at 20 degrees should all be similar values. And if they're not similar values, we can exclude ones which are outliers or anomalous results. But what we can do then is calculate the average rate of reaction at different temperatures. Now, in order for this to be a fair test, we have to think about control variables. And control variables are essential for a fair test. So if we're changing the temperature deliberately as our independent variable, all the other variables within this protocol, within this experiment, need to be kept exactly the same each time so that we can compare the results fairly. So what I want you to do is pause the video here and just think about what the control variables are. You might want to look at the booklet, and the practical is set out in the booklet for you. I think it's page 7 or 8. So have a look at that, pause the video, think about the control variables, and once you've got yours listed, restart the video and see how many you manage to identify. So these are the key control variables. What we want to make sure is that the volume of the amylase is the same every single time. So we're using the same quantity of the enzyme. Not only the volume of amylase needs to be kept the same, but also the concentration of the amylase. So if we use, for example, I might add 10 grams in 100 centimeters cubed of water, and I mix that together, that's going to give me a concentration. Sometimes in chemistry, you might have come across molar concentrations. So the concentration of amylase might be 0.5 molar, and we want to make sure it's 0.5 molar every single time we do the test. The volume of amylase might be 10 centimeters cubed, and we want to make sure that we use the same quantity, 10 centimeters cubed each time, and we measure the volume by using a measuring cylinder. In a similar way, we want to make sure that the volume of starch is kept the same, and also the concentration of starch is kept the same. The time between tests also needs to be the same, but that's part of the protocol. The one thing that you might not have thought about, and if you did, really well done, is that we also need to control the levels of acidity or alkalinity. We need to control the pH. So just to remind us that the pH scale goes from pH 1 all the way up to pH 14. pH 1 is a really, really strong acid. pH 7 is in the middle, and pH 14 is a really, really strong alkali or strong base. And here you can see examples of where you might find these different types of pH values. Now, we want to do our experiment at pH 7 because pH 7 is neutral, and most enzymes are going to function best optimally at pH 7. Now, we need to think about how do we make sure that the pH is pH 7 every single time. And what we do is we use these things here, which are called pH buffers. They're basically liquids, very, very complicated but interesting chemistry. But if I put something in this one, for example, this is pH 4, then whatever I put in there will become pH 4 and it will stay at pH 4.